Hey, turn with me to that next section in the book. And give you a little.
Do you have the assignment sheet?
Yes. Wait. Maybe. Yes. Is that everybody? Okay, guys, we are going to be doing a huge topic in Apcalc right now. Okay, so this whole section is going to really complete, it's going to put together probably 85, enable you to put together 85% of the AP test, maybe even 90. The last little part after this, and remember, it's end of January. All we do is this section and then area and volume. And we're done with calculus. And then I'll spend 6 to 8 weeks or whatever time we have left. Well, I think we're a little bit behind. Whatever time we have left, we're going to review the crud out of it, kind of go back through the whole course again, doing like a mini section on limits, mini section on derivative, mini section on integration, and then practice test, and get you ready. So, got a new poster up, kind of inspiring you guys, right? Okay, so I get bored sometimes late at night here.
Did you make this one as well?
I did.
With your little face on it?
With my face on there, yeah. It was Lance Armstrong, which for a while was a great poster. And then when he kind of turned out to be a fraud, I was like, man, what do I do with this poster?
Huh.
And again, late at night, I was like, huh.
That was really. So are you calling yourself a fraud?
Yeah. No, now it's not Lance Armstrong. Now it's Mr. Hurry. So a thinned down version of Mr. Hurry on a bike in the Alps.
Look at this dude. He's like.
Yeah, he's a little shirtless. Yeah. All right. So anyway, guys. So what we're going to be talking about today, you're actually, if you take physics right now, and you're already in my class, we already know how to integrate, don't we? So I can give you a function. Well, yeah, somebody's like, yeah, that's debatable. But hopefully you already know how to integrate at least at a pretty decent level. And even if you're struggling some with that still because you didn't learn it directly from me and you're a little bit late on that, that's going to come together. You're going to have a lot more time to get that together. You need to kind of right now unlearn that. So there's a huge topic. What I mean by unlearn it is I'm going to be giving you integration problems in this chapter, and you're not, for part of it, you're not going to actually use those integration rules. What you're going to start to learn right now is that when you integrate a function, what you are actually doing is not finding a slope like a derivative finds. You're finding the area between that function and the x-axis. And if that area, and we're going to talk about all this, but like that process is you're going to be accumulating that area. Now, sometimes the area you find is actually a positive value. And we're going to talk about this a lot. As you accumulate from left to right, area for a curve over the x-axis is positive. But area from a curve below the x-axis up would be negative. Or if I go this way, it's kind of the opposite. We're going to talk about that. But today, and with the ways we accumulate that area, sometimes I can look at it and go, well, I can tell exactly what that is because that function was linear and it made a triangle. And I know how to find the area of a triangle. Or I'm looking at this and there's a semicircle there, and I know how to find the area of a semicircle. So a lot of times we're going to just pull out our geometry and actually accumulate those areas. Today, we're going to start a process called a Riemann sum. And it looks like Riemann or whatever, and you can see some of those on there. But what Riemann did is he found a way to use rectangles, and we're going to start very basic, and to take rectangles or trapezoids and to fit them under the curve and approximate area that way. Now, the problem with rectangles and trapezoids is they have a flat top on them, right? And curves don't have a flat top. So as I use those rectangles to fill it in there, I'm going to be off a little bit. Well, that's why a lot of this process is called approximation. And it seems silly to approximate that way, but what we're going to do is we're going to learn how to actually find these Riemann sums, and there's different kinds. There's a left hand, a right hand, a midpoint, and a trapezoid. We'll talk about all four of those today. We'll practice them tomorrow, and then we'll get into the accumulation thing. But this is a huge topic, very, very doable, shows up all the time, just all the time. But we're going to learn how to approximate that way, and then we're going to take what Riemann really did, was he took these, and where Newton came in, he took these rectangles, and you'll see this, the more rectangles I fit into the curve, like for instance, if I have a curve, and I'll show you this in a second, if I have a curve that does this, and I say you only get 2 rectangles, you're like, well, I can fit a big one here and a big one there. That's not going to be very, very good approximation. But if I fit a bunch of tiny little skinny rectangles in there, then when you put the little tiny rectangles in there, they can fit better. Well, the more rectangles, the closer you get to being perfect. But the more rectangles, what happens to the base of those rectangles?
Skinny.
They get smaller, or maybe they approach 0. So you start working limits into this problem, and you say, well, as I approach an infinite number of rectangles, my bases of each rectangle get smaller and smaller and approach 0. And when I sum all those with sigma notation, I end up getting an actual exact area. And that's the whole idea of these Riemann sums. But AP, and I actually remember learning this in calculus in college, but AP actually makes you show that you know the Riemann sum. So even if you know how to integrate and find the exact area, they don't care. They'll say something like, find a Riemann sum, or using a left-handed Riemann sum with 8 rectangles, approximate the area. So if you actually found the exact value, no credit. You got to show that you know how to approximate using these methods. So that's what we're going to start today, is the Riemann sum thing. So the whole topic, the whole area is approximation and accumulation we're going to talk about. And then when we finish this up, we're going to get into actually what the fundamental theorem of calculus is. And there's 2 of them. There's the fundamental theorem of calculus, which some people call number 1, which is the one that you probably already use if you are taking physics. And have y'all done integrals where you have a little number at the bottom and a little number at the top? Anybody in physics? Have you done that?
Yeah.
Okay, that's a definite integral. To do that, you apply the fundamental theorem of calculus, whether you know it or not. So some of you have seen that a little bit, but we're going to extend your knowledge of it, right? And then also, there's another fundamental theorem of calculus we call number 2 that we're going to look at as well. And once you know that, man, the doors are open on these problems. You can start doing so many different things, and I can start throwing so many different things at you. Because after that, all I have left is area and volume, which honestly isn't even, very little of that is even in Cal 1 in college. Usually it's Cal 2. So everything we do with area and volume, in fact, last year they just said, oh, don't bother, we won't even test you on it, on that little shortened AP version they gave last year. Because again, it's not a Cal 1 topic at most schools. Most schools it's Cal 2. So from that point on, you'll be getting a head start on Calculus 2 should you be a mathematician or an engineer or statistician or anything like that. All right? So anyway, so here we go. Accumulation. What we're basically doing right here, and you can read through all this, but we're going to be estimating areas below curves. So if you want to read through that, you can. I'm saying much of what I've already said, but I'm giving you right here an actual curve. This is the x squared plus 1 curve. If I would have graphed the whole thing, it'd be a big parabola shifted up 1. And what I want you to do is integrate this from 0 to 4. Now, like I said before, when you integrate something, what you're really doing, I don't want you to use your formulas. I want you to use this whole Riemann sum kind of thinking. What you're really doing is finding the area below the curve, between the curve and the x-axis. And by the way, you'll hear me say this. I'll say area below the curve. That's when you ask a mathematician, what does an integral mean? They're going to say, oh, the area beneath the curve. But technically, it's not beneath, because this one would be beneath. But if this curve was below the x-axis, what's beneath? That would go forever, right? So when we say beneath the curve, and I think on my new notes, I actually put that in italicized. Yours is not like that. The area under the curve really means the area between the curve and the x-axis. right? So let's just start with that. So this area right here, you can see, I don't know exactly what it is. I mean, if somebody asked me to approximate it, I mean, I could come in here and start counting squares, right? If this is up 2 and that's a half, what does each square represent? What volume? I mean, sorry, what area does each square represent if you're right, if that's 2 and that's a half? 1. So you could actually come in here and say, all right, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I got 18 whole squares. And then you could start kind of eyeballing it and say, okay, 18, maybe that part and that part gives me a 19. Maybe this and this give me a 20. Maybe that and that little part give me a 21. Maybe that and that fills in gives me a 22. Maybe that part would fill in that to give me a 23. I think if I haven't lost count. And then maybe that filled in there would give me a 24. And maybe that and that, maybe a.
Oh, you already counted that little corner.
Well, I didn't dot it.
You didn't dot it.
There's one at the top.
So maybe close to 25. I don't know if I haven't lost count. So if I was just eyeballing it, had to figure that out, that would be one way to do it. A better way to do it would be actually integrate the x squared plus 1 function from 0 to 4, although we haven't talked directly about that yet. But if I didn't know that, if I didn't have calculus, this is kind of the process I would use. Now, the actual area of this, so I estimated about 25. The actual area was 25 1/3. So actually, I was pretty close, just eyeballing that right there. And that's me using calculus, the actual integration process. Say it again?
That wasn't you using calculus. That was you just counting.
No. Me counting got me 25. 25 1/3, the actual value is me going and using calculus from 0 to 4 that I didn't show the work for. Okay? So if I actually found it. Now, here's what Riemann said. He said you could use rectangles to approximate it too. Now again, loosely you're like, if I used rectangles and I went, well, I could use this rectangle from 0 to 2 and just come up. This is called a right-hand rectangle, where you pick up, like if the total space is 4, if I'm only going to use 2 rectangles, I split it in half. So 2 and 2 would be my bases. And you basically bring up the height until the right side of the rectangle hits the function. So you bring that up until the right side hits the function, and then you just bring it over. You bring this one up until the right side hits the function, and you bring it over. And that's an example of a right-hand Riemann approximation, which clearly stinks, right? Because I've got all this extra area that I really didn't want in there. Okay, but let's be honest, with 2 rectangles, it's going to stink. But look what happened if I went to 4 rectangles. With 4 rectangles, I split the base, which is a total width of 4, into 4 parts, which gives me 1, 1, 1, and 1. And then I bring up the rectangle till the right side hits, right side hits, right side hits, right side hits. And you can see when I actually calculate those areas, by the way, I didn't mention that in the first one. To calculate the area, you go base times the height. Base times the height, right? Base times the height. And you would add all those base and heights together, right? Base height, base height, base height.
What's the difference between like the right hand and the left hand?
Well, I'll get to that in a second. So I'm just focusing on right hand right now, but you'll see in a second, it's no big deal. Well, I'll tell you. When you bring it up, instead of bringing it up till the right side hits, you bring it up till the left side hits. And then I'll talk about midpoint and trapezoids, because trapezoids would be much smarter to do. But again, you're going to be asked to do different kinds, and you have to know how to do all of them, not just the one that makes the most sense. Okay, and if you're thinking to yourself, this is stupid, why would you do this? I would tend to agree with you. But when you actually see the algebra of this, and when they turn this into a limit problem, where the base shrinks smaller and smaller and smaller towards 0, then you see that it actually becomes a calculus problem. And that's where the calculus comes from. But what happens, and by the way, how do you find the heights of all of these? You could count them, but sometimes that's not going to land on a nice, neat whole number. But you could plug that x value back into the function, right? Remember, I knew the function was x squared plus 1. So if I plug 1 in there, I get 2. If I plug 2 in there, I get 5. 3, I get 10. 4, I get 17. Right? So once I have all of those, look, 34, still way more than 25 and a third, right? Why? Because look at all that excess. I have over approximated, and clearly that's going to happen when I do right hand approximations with increasing functions, right? Are you with me? Now look what happened when I went to 8 though. Now again, I had to change the base, right? So if the total width is 4, and I divide that into 8 parts, now each base is a half. So I take each area, which is base times height all the way through, and each height, and I now multiply each of those together to find the 8 little areas and add those together. Okay, now as you've seen, and then this area ended up being 29.5. So what's happening to my area as I go from 2 to 4 to 8? It's getting closer and closer to the real value, which is 25 and a third, which again, you're taking my word for. And you can only assume if I do more and more rectangles, I have less and less excess, don't I? Right? And that gets me closer and closer to the true approximation. Now, AP is going to ask you to do these kinds of Riemann sums. So you want to show your work, okay? And to show your work, you can either say, all right, I'm going to take the base, which is, in this case, 1/2, and I'm going to multiply it by the height, which is f of 0.5, because I plugged the 0.5 in, right? If I plug a 0.5 into my function, that gives me the height, and you multiply them together. And you show those steps right there, and we'll go over that, and you'll see that. You show the steps, and then you just put your answer in. But if you just put an answer, you get one of the 2 points. You have to show them what you're doing to get these. You seeing that? Okay. But anyway, the situation here, you don't always have to draw pictures of these, but you do have to be able to calculate what you're actually doing. Okay? And you need to show these calculations. So if you need a picture at first, which I'll probably do with you, or at least draw something representing the function, even if it's not accurate, just so you get a visual of what's going on. But at some point, you need to be able to do these approximations. And this particular one was a right-hand Riemann or Riemann sum. Is everybody with me at this point? Don't be shy. Anybody have a question? Okay, so right here, let's just do a couple of these and see. I'm looking at number 1 at the bottom of that page 86. And it says, okay, you've got this function, right? And I want to approximate the area under the following functions. And again, I use under very loosely, okay? And most of the functions I give you initially will be all positive values of y. So they'll be all above the x-axis. So we won't have to worry about what happens when it dips below. That's for another day, okay? So right here, I've got this function. Now, we just graphed x squared plus 1. So x squared plus 3 looks pretty similar, doesn't it? Okay, so I'm just going to represent that x squared plus 3 right here by just some random function. But I'm finding the area from 2 to 14. Are you with me? So from 2 to 14, actually the graph looks something like this. I'm just going to say, all right, that's 2. And if this function keeps going up, let's just say that's 14. So I want to find all that area right there using this Riemann sum. Now, the way you write this is important to AP. They want to see that you understand area. So how does AP calculus or any calculus represent area? With the what? That's geometry. How does calculus do it?
Area integral.
The integral. So what you're going to do is say, okay, I'm going to approximate it. I'm definitely approximating. I'm not actually doing the math, but I'm going to write the integral of this function dx from 2 to 14, and then I'm going to show my approximation. Okay? So you're labeling it. You're telling it. Just like if I was finding slope, I write dy dx at blah. This is saying area. But I'm not going to actually go and find the integral of that, which is x cubed over 3 plus 3x plus c. I'm not going to do that. That's for another day. This is our approximating what that would be. Now, how many triangles, rectangles are supposed to have? 6. So what I'm going to need to do is take this whole this distance from 2 to 14, which is 12, so that the base I'm going to find, I'm going to go end minus the beginning divided by 6 to find the base. And on this first problem, very nicely turns out to be 2. And you can expect bases to be 1 or 2 or a half Rarely are you ever going to get a base that's uglier than that on the AP test. They try to make it pretty basic for you for the base. Okay, so each base has a length of 2 when I split this up. Now, we're doing a right side rectangle. So when I plug in to find the height, again, I'm going to be picking, say, from 2, since the base is 2, from 2 to 4, right? I'm going to be plugging what number in, the 2 or the 4 or something else? The 4. So I'm going to be plugging in the 4 into my function. Are y'all with me on that? So what I would show on my AP test is base times f of 4. That's base times height. And then I would say plus the next base, 2. What would the next height be? 2 more over from that. So you're going to be plugging f of 6, or 6 into the function. And then 2 times f of 8, 2 times f of 10, 2 times f of 12, and then finally 2 times f of 14. And those are your 1, 2, 3, 4, 5, 6 base heights. Is that making sense so far?
It's a really long problem.
It is long. And also, and that's another thing I want to mention, you go take this class in college and they'll say, all right, do a Riemann approximation with 14 rectangles. Not in AP. 6 might be the top end. So I asked you to do 6 and 8 right here. On AP, it's like 4, 5, 6. Rarely is it going to be anything more than that. I mean, truly, rarely are you going to see anything more than that. So it's really more about the process to them, showing your setup. Now, I still have to do the algebra of actually finding those heights, right? Now, AP a lot of times won't give you the function. They'll give you a table of values. So you'll have a table that will have X and Y values, right? And the Y values represent those heights. I love those. They're spoon feeding them to you. You don't have to actually find them. So be ready to use lots of tables and charts. I will give you plenty of practice with that as well. So let's go ahead and find these. This is not too bad. I've got 2 times, what's f of 4? F of 4 would be 19. So that part's 38. And then show your math. What's f of 6? 39. So that's a 78. F of 8 would be 67. So that's a 134. F of 10 would be 103. So that's a 206. F of 12 would be 147. So that's a what? 294. And F of 14 would be 196 plus 3, 199. And that would be a 398. And then you would now just have to add all of those up and just write down whatever you got. And that would represent the approximated area of that. And you would get credit on the AP test for showing that answer and for showing this right here. That's what you get credit for.
You don't necessarily have to do 2 times that.
You honestly, you probably don't have to do that. But again, I'm a big fan of showing as much work as possible. So if I accidentally found f of 4 to be 17, they would look at this and go, well, they didn't know what they were doing there. But if I said f of 4 and then 17, they'd go, oh, they just can't do algebra. Let me give them a half point maybe. So the more you show, the better. But typically, it's show the setup and the answer and 1 point for each. So just because you get the answer doesn't mean you get both points. They want to see the math. Are you with me on that? Now, also, on all of these problems, when you are in charge of picking the base, the bases are always going to be equal. But AP realized long ago that there are people that make little apps, little formulas, whatever, that you can just plug in formulas, plug in number of rectangles, and it spits out the answer. So what they started doing is giving you tables where the X values that you're plugging formulas that AP uses, and formulas you'll see in a textbook. Like, for instance, they will use this formula. Instead of writing the base every time, they'll go, well, since the base is the same every time, why don't we just factor out the base and then just do f of 4 plus f of 6 plus ... through f of 14. And then when we add all those together, we'll just multiply by a 2. That's fine if the bases are the same. And today the bases will be the same a lot. But again, AP finds a way to keep you from being able to do that kind of stuff when it's a calculator problem. All right? Y'all with me? Okay, real quickly on number 2. I'll tell you what, are y'all with me on that? I want to show you some different examples. Okay, so let me show you some other situations too. I'm just going to move on to this. Some other situations that aren't just right hand. So again, here's an example of a random function. This is a parabola going downward, and I wanted to find the area between 2, under the curve between 2 and 10. And I want to approximate it with different techniques. So we've already talked about right rectangles, and you can see that right rectangle situation right here, where you go from 2 to 10. If I were to use 4 rectangles, right, split that distance of 8 up, so you got a base of 2, 2, 2, 2, and you bring up the height of the right side. Sorry, that's the left side. Right here, you bring up the height of the right side until it hits. So you're finding those 4 heights, right? And you can see on this one, right here, I had a slight over approximation. But here I under approximated, way under approximated, didn't I? Now, a left hand approximation does the exact same thing, but it just brings up the rectangle until the left side hits. So when I do that, this one's going to under approximate, but this one's going to over, right? So for the net result, this is probably going to calculate, we're definitely going to calculate too much area. This is going to calculate too little area, right? So some people came up, well, not some people, Riemann came up with, well, what about a midpoint approximation? A midpoint says, what if that's my base, let me just go to the midpoint. He said, if this is my base right here, 2, I'm going to go in between the 2 and the 4 to 3, and I'm going to plug that in to find the height. So basically, I'm going to bring it up until the middle x value hits there. So on this one, I'm not just going base times f of 2, like a left would, or base times f of 4, like a right would. I'm doing base times f of what?
3.
Which is the what?
Middle.
Which is the, rhymes with paverage.
Average.
Average of those 2. So I would actually average the 2 x values on either side to get the x value that goes in. Are y'all seeing that? Yes, no? Yes.
When writing out that sum, would you have to include that part, or could you just write it like?
If you were able to see it, no, I would just go 2 times f of 3.
All right.
2 times f of 5. But sometimes you're going to need to be able to average those 2. Are y'all with me so far?
Right.
And the charts is kind of weird the way that works, but we'll talk about that later. But the best way, and you can see on this one, this is a little bit better, because this way, when I bring it up, each time I usually get a what here on the left? An over, but also an under on the left. So here I got an under and an over, under and an over, under and an over, and usually those balance out, kind of cancel themselves out. Not perfectly though, because it's a curve. It's not like it's linear, right? If it was linear, it'd be nice and perfect. But if it's a curve, it's going to be better. And then somebody, Riemann, came up with a trapezoidal one, and a trapezoidal says, well, rather than average them, why don't we just bring up the rectangle until the left hits and stop it, and then let the right side hit and stop as well, which actually makes a trapezoid. Now, do you remember the formula for a trapezoid?
No.
I don't either, or didn't used to know it. I learned it like this, though.
Break it up.
I learned it as 1/2 times, this was base 1, this was base 2, and then this was the height. So even if it went like this.
Oh, isn't it like 1/2 base 1 plus base 2 times height?
That's right. 1/2 base 1 plus base 2 times the height, which is essentially the average. Don't write this down. The average of the bases times the height. Now, here's the problem. We don't look at trapezoids that way because ours are always turned up going this way. So it's not the bases that we're averaging. We only have one base. We're averaging the what? The individual heights. So our formula is the same thinking as this, but we're going to be doing this. 1/2 average of the heights. I'm sorry. 1/2 the sum of the heights times the actual base, which is the same thing. You pick how you like to do it. The average of the heights times the base. I normally write it like this. I normally write either 1/2 base, add the heights, or I write base times the average of the heights. And that's how AP usually sets it up. And that's how I wrote it when I set this up for you. So those are trapezoid approximations. And again, to find each height, what do you do every time? You got to find the x values and plug them into the function to find the y value. The base you're going to figure out at the very beginning, because you're going to go 10 minus 2, which is a total of 8, and divide it by how many rectangles you need. And that's going to be your base you're going to use. Y'all with me so far? Okay, so if you want to look at examples of all those, I've written them out. Like there's the left, there's the formula for right, there's the midpoint one where you have to average the x's and then plug it in to find the height. And then there's the formula for trapezoids where you actually average the heights and then multiply them by the base. Okay? And I normally write mine 1/2 base, sum of the f's. But if you want to go base times the average of the f's, that's fine too. It's just up to you. Okay? So I think a lot of you guys, does anybody have a question right now? I want to run through some examples in the time we have left, which is not much. And I'll probably just pick a couple random ones for you to see. So if you jump to, I'll tell you, let's just look at the homework. Day 1 homework, if you look at this, I've asked you to do a couple problems. But the first one says, all right, for number 1, A, B, C, D, I'm giving you this function. I'm telling you I want to go from -4 to 12. I want to do 4 rectangles or trapezoids, and I want you to do 1 of each kind of problem. Okay, so let's just check it out. So this first one, the area, which again I would represent by the integral of the function dx from -4 to 12. You don't have to write that every time, but that's what you would do on an AP test. Now, if I'm doing the first one is a left rectangle. Okay, now visualize this function. Let's just pretend here's my function right here, and I'm going from -4 to 12, right here, and I'm finding this area. If I'm doing a left rectangle, what x value goes in first? Because remember, on a right rectangle, I didn't start with -4. I went to 1 base over and plugged that in. Are y'all with me on that? Now, my base is clearly what? It's a total of 16, right? That minus that 16 divided by 4. So how big is my base? 4. So I know I've got a base, which is base times height, yada, yada, yada. I know my base is 4. My height, I'm going to begin on a left rectangle with which value? -4. So I'm going to plug in f of -4. Are y'all with me? Yes or no? On a right rectangle, I wouldn't have started with -4. I would have started with 0, which is 4 over, because the base is 4, right? So I would have gone 4 over. Remember, I'm doing 4 rectangles. I would have started at 0 and plugged it in. But you can see right here, when I come up, I'm going to stop right there. That's the one I'm using on the left. Okay, so what would the next one be? Base times f of 0. And the next one, base times f of 4. And then the next one, base times f of 8. Do I do f of 12?
No.
No, because f of 12, the left side, that would give me a whole nother term. And you can already see that I've got all 4 there. So all I got to do now is find each function. So I know I didn't give you much room here. 4 times, what's f of -4? 16 plus 12 is 28, and 4 is 32. And f of 0 is 4. And f of 4 is 16 minus 12 is 4 plus 4 is 8. And f of 8 is 64 minus 24 is 40 plus 4 is 44. and you would add all that up, and that would be your left-hand approximation, which is most likely not great. Are y'all tracking with me? And what would be the difference between this and a right hand? On a right hand, I don't start with f of negative 4, do I? I start with f of 0, but what do I end with? 4 times f of 12. Good. All right, let's just set up these other two. What about 1c says midpoint? So on the midpoint, remember what I want. I want the y value in the middle of what for the first one? In the middle of the negative 4 and the 0? So you're going to average the negative 4 and the 0, and what are you going to get? Negative 2. So you're going to be using negative 2, positive 2, positive 6, and positive 10. Those are going to be your x values that you plug in, right? So on that approximation, and I'm going to, well, I'll go ahead and do it. So for C right here, you're going to go same base, but f of negative 2, because it is the average of those two x's. And then another base times f of positive 2. Why? Because it's the average of the 0 and the 4 that I'm plugging in. And then next, 4 times f of 6, because it's the average of the 4 and the 8. And then lastly, 4 times f of 10, because it's the average of the 8 and the 12. And I plug that x values in the middle to get those middle y values. And now my approximation looks more like that. So each one I do, I get a slight over and a slight under. And the idea is that it balances itself out. Y'all tracking with me? And then, of course, you got to find these values, right? You with me? So I could go back and do that, but I just want to make sure, and I'm running out of time, big time. So real quickly, last one, trapezoids. What's a trapezoid want to do? It doesn't want to average the x's and plug it in. It wants to average the what?
Y.
The two y values. So on the trapezoid, you're going to go same base, but you're going to go average f of what?
4.
So you're going to take the f of negative 4 and the f of 0 and average those together. Or you can go 1/2 times the base and just add them. And then you move to the next one. 4 times, and you're going to average the f of 0 and the f of 4. Average those. And then you're going to take the base, f of 4 plus f of 8. And then lastly, f of 8, f of 12. So tonight, see what you can do on this homework problem. We've already kind of knocked out that first part. See what you can do on these. And if you don't get the chart stuff or whatever right now, don't worry about it. If there's some tables, we didn't have time to get through everything I wanted to get through. But we'll definitely finish this up. I don't think we're doing anything new tomorrow except more practice with this stuff. All right? Good day? All right. Go ahead, Apcalc.